Good morning, everyone. Welcome to today's Monash Software Systems and Cybersecurity Seminar. We are very happy to welcome Dr. Feng Liu from University of Melbourne. Dr. Liu is a machine learning researcher with research interests in hypothesis testing and trustworthy machine learning. He is currently a lecturer at the University of Melbourne, Australia, a visiting scientist at RIKEN Japan, and a visiting research fellow at AAI UTS Australia. He has received the Outstanding Paper Award of NeurIPS 2022, the Outstanding Reviewer Award of the same conference in 2021, the Outstanding Reviewer Award of ICLR in 2021, and UTS Best Thesis Award as well. And until now, he has published over 50 papers in high-quality journals or conferences, such as Nature Communications, IEEE TPAMI, IEEE TFS, and ICML, ICLR, and so on. I'm not going to read all of them, and today he's going to talk to us about recent advances of TwoSample testing and its applications in AI security. Thank you, Feng.
Yes. Thank you, everyone, and thanks for the kind introduction from Mohammed. Okay, now let's start. Today we'll talk about the recent advance TwoSample testing and its application in AI security. Okay. First of all, let's review what's the aim of TwoSample testing. Why do we need to compare two distributions? Yeah. So look at this figure. If we can compare two distributions are the same or not, we can say if this kind of treatment have the effect before the treatment and after treatment regarding our blood pressure. And if we use TwoSample testing, we can also compare if two sets of images are from same distribution. Yeah, here we show the very easy example. It's maybe one set of images from dogs and another from fish. So using TwoSample testing, we know they're definitely from different distributions. Yeah, and if we look at more about the current classification problem, it's about means, the digital handling classification. So if we use TwoSample testing, we can tell if the generated means and the real means are from different distribution. Yeah. So using TwoSample testing, we can tell if two sets of distributions are same or two sets of samples are from same distribution. That's the original aim of TwoSample testing. Yeah. Okay, and if we consider recent advance in AI security, in AI field, we know we can also use TwoSample testing to help us distinguish between the human writing texts or GPT writing texts. Yeah, because they definitely have different distributions. And similarly, we can use TwoSample testing to tell if this set of image are from human created or from AI created, because AI created images and human created images, they are from different distributions. Yeah. Okay, and then we can talk about why the TwoSample testing matters in the machine learning area. TwoSample testing is there from the statistical view as to compare two distributions or to compare two sets of samples. Why it matters in machine learning? Okay, now let's say the very simple scenario in machine learning area. In machine learning algorithm, we always have a training set, right? Like this guy. And for this training set, we can have the ground truth decision boundary between the two classes here, okay? And then we can train a model based on the training set, right? Its model can be neural network or CNN. After that, we want to apply the trained decision boundary here, apply this boundary to the test set to help us to classify the upcoming instance here, right? Yeah. From this figure, we can say the training set boundary, after we train, can help us distinguish between two classes data here very well, right? We can say the trained decision boundary and the true decision boundary of test set, they are overlapped, okay, here. However, this kind of phenomenon is based on the basic assumption in the machine learning area. This assumption is that the training and test set must have same distribution. Okay, what will happen if we do not have this kind of assumption satisfied in our data set? we will talk about later. And first we will show a real example. In the SML19, researchers proposed another test set for CIFAR10 data set. It's called CIFAR10.1. Okay. Now we actually have a question here. So can we use a model trained with CIFAR10 images and apply this model to classify images in CIFAR10.1? Yeah, here we need to answer a basic question. If CIFAR10 and CIFAR10.1 from same distribution, right? If they're from different distributions, actually in theory, we cannot guarantee the performance or the generalization ability of the model trained with CIFAR10 in CIFAR10.1. Okay, yeah, so that's a key question. Can we do that? Okay, and then we can say what will happen if they're from different distribution. Okay, now we can use a simple example. Here, on the left side, it's our training set. And on the right side, it's a new test set. And for this test set, we have a new decision boundary here, okay? And we can say this test set actually have different distribution compared to our training set, okay? So what will happen if we just apply the decision boundary from this side to the test set, to our new test set? Yeah, we will definitely misclassify this kind of samples here, right? Misclassify this kind of instance here. And it will cause the significant error, okay. Actually, a more modern or representative example is adversarial attacks. In adversarial attacks, I think all of you should know that, okay? In adversarial attack, we will add a specific noise and we will get a new image, right? Compared to previous image. And this image, human cannot recognize the difference, but for the classifier trained with our original data, will recognize this panda is given with very high confidence. Okay. So why is this will happen? The main reason is that in our second work I will talk about today, the main reason is that the adversary example and the nature example, they're from different distributions. Yeah, that's why it will cause a very high error here. Yeah, significant error here. Okay.
Feng, there is a question in the chat. It's asking, can the method be used for CAPTCHA? TwoSample testing.
CAPTCHA, sorry, I'm not sure what I know the.
To verify if you are human or
not.
No.
Ah, okay. Okay, yeah. Yeah, I think that's a very interesting question. If we want to use it for capture, I think we need we need a lot of data regarding the human behavior. Yeah. So if we have this kind of thing, we can say if the image you select or the behavior you have a different distribution compared to the human behavior or not. Yeah. But I think it's we need to build it from scratch, right? Yeah. Maybe not just for the capture, but from other systems. Yeah. If we want to build other system to do the same thing, yeah, we can use this kind of TwoSample testing. Yeah. But for the current system, I'm not sure. Yeah.
Okay. Yeah. Thank you.
Yeah, thank you. Okay. So from previous slides, we know it's always important to test if our training and test set are from same distribution, because if the test data distribution is different from the training data distribution, we actually cannot rely on our machine learning models, right? It will cause significant error, and the adversary examples is a well-known example, actually. Yeah. Okay, and then we can, we can quickly go through the representative papers in TwoSample testing field. In 2012, Asgriton, they proposed a kernel TwoSample test. It's the first time we can consider TwoSample testing on the very high dimension data instead of just one dimension data. Like I think well-known TwoSample testing like KS test is mainly focused on the one dimension case. And the kernel TwoSample test can make us consider more complex scenario. And in the same year, they proposed how to choose the best kernel for the two-sample testing. And then Widwa, he proposed interval distribution features, like we can know which feature is more important to see the difference between two distributions in 2016. And in 2017, one work considered to use a classifier two-sample test. The idea behind classifier two-sample test is very easy. If the two sets of samples are from these different distributions, yeah, we might use a classifier to just classify them, right? And I will talk about later. And in the same year, and Danica proposed a more advanced kernel two-sample testing. Yeah, and between the 2020 and 2017, and I think the area they focus on the goodness fit testing. It's a different story. And in 2020, we go back to the testing, two-sample testing problem, and we propose learning deep kernels for non-parametric two-sample testing can enable us to handle more complex data in the high dimension, like images. And in the next year and last year, we propose more testing methods. And in 2021 paper, we propose how to use two-sample testing to say to detect adversarial attacks. And actually in the previous paper, the Nicholas Kalin's paper, he mentioned that the adversarial data and the training adversarial data and nature data, they have different distributions, but such a difference is hard to tell using the statistical tools. And in this paper, we actually find that they use like the very low power two-sample testing and makes that claim. Okay, and we find that actually two-sample testing can be very sensitive to detect the adversary examples. Yeah, and because we already use a deep kernel, so in the last year we also proposed the more robust testing methods. We consider if attackers know you use deep kernel, so maybe he will attack our method, and we propose attack and defense method for non-parametric two-sample testing. And in this talk, I will focus on the 2020 paper and 2021 paper. Okay. Okay, it's a first work. It's my good fortune to work with Wen Kai, Jie Guangquan, Arthur Gratton, and Danica Sunderland. Okay. Yeah, first I will introduce some basic knowledge for the two-sample testing and two well-known two-sample testing methods. In two-sample testing, we actually have two types of methods. The first is called parametric one. In the parametric one, we already assume we know what kind of distribution our data follows, like all our data follows a Gaussian distribution. So unless we need to test the mean or test the variance, okay. Another is called non-parametric. We do not assume we know what type distribution our data follows. Okay, it fits our real-world data side, because for complex one, we actually cannot assume it follows Gaussian distribution or something else, right? So it's a non-parametric two-sample testing. And in the two-sample testing, there's where we often have two sets of samples. Here we call X as a set of sample and Y as another set of sample. Okay, and our T is a statistic. Okay, this statistic is actually a function, and this function will take X and Y as input and find an output of a real number, the little t here. Okay. And in the two-sample testing, if we already have a statistic, we call T here, the capital T here, okay? And then we can use a permutation test to say if two sets of samples are from same distribution or not. Okay, let's say this example. What's the permutation test based on the meaning of the word? We just permute, okay? At previous slides, you can say we have X and Y here, okay? X and Y here. And then we permute the instance X and Y, okay? And we can generate new X1 and Y1, okay? X1 and Y1. It's like we merge X and Y together and we just permutate. And then we just split it to half and generate X1 and Y1. And we use the same statistic, we can obtain the little t1, okay? Yeah, we permute once. In permutation test, we will permute a lot of times. Here we permute capital N times. So we will obtain T1, T2, little T1, little T2, until little T capital N, okay? Okay, now we have this capital N values here, okay? So, and we also have the original T here, okay? Original T here, and we have this capital N T's here. So in permutation test, we will compute what's the percentile of this little t in this series, okay, yeah. Oh, sorry, yeah, in this series. If this capital T if this little t's value is very high, in a very high percentile, say in the 99 percentage within this series, we will say, okay, we will say the X and Y from different distributions, okay? Because normally the smaller t will means they get closer to each other, okay? Yeah, so it's a permutation test, So this is a permutation test. In permutation test, we have X and Y, and we have the statistic T, okay? So based on these three values, or two sets of samples and one function, so we can actually tell if they are from same distribution or not, okay? Yeah. Okay, it's a permutation test. And then we will introduce two well-known statistics. Okay, in previous we have X and Y, and we also have a statistic, capital T, okay? And then we will introduce two well-known statistics, okay? The first is called Kernel MMD. MMD means maximum mean discrepancy. It's from Dulles lemma. In this lemma, it says that if P and Q, they are equal, if and only if this kind of expectation, they are equal, okay? And here we actually map X using F, and we map Y using same F, okay? And this F is a bounded function. If for any F, or for all this kind of function F, these two expectations are the same, we will say P and Q are from same distribution, okay? It's like, no matter what kind of F we use to map our original data set, after mapping, their mean value is still same, or their expectation value is still same. So we will say P and Q are from same distribution. Okay, yeah. So it's a Dulles lemma, and so based on this lemma, we can give the very basic definition of MMD. Okay, so how to compare difference between two distributions? We can just use a difference between these two expectation values, right? Yeah. So we can get a very naive definition here. So it's a first expectation value minus second, and we got the soup norm here. Okay, yeah. And we know this kind of MMD, if this guy is equal to 0, it will mean for all the bounded function F, these two expectation values are the same, right? Are the same, yeah. So we can say the P and Q from same distribution. However, this kind of term has an issue. It is not a good term to estimate, right? Because we have soup norm here. We cannot use the max to estimate it because it is not unbiased and it is not consistent. Okay. However, if we limit this kind of function class F to be a uniball in reproducing kernel Hilbert space, we can compute the soup analytically. Okay. And this is proposed in the 2012 paper. It's called Kernel TwoSample Test. Okay, now if we introduce a kernel function K here, so MMD can be just compute using this kind of formula. Okay, it's just K is a kernel, characteristic kernel, like Gaussian kernel or Laplace kernel. Okay, and got expectation for this kind of value. Because here we use a random variable to represent instead of the distributions, so we actually can get the estimator for this kind of thing. Okay, yeah. So and then we can give the very naive introduction to compute the kernel MMD. Okay, in kernel MMD, we have the kernel matrix. This kernel matrix to measure the similarity between samples from X and Y, okay? So this area is called KXX. It's just to measure the similarity between instance in the X in the first sample. Yeah, okay. And then, so what is the value of MMD? The MMD's value is equal to the mean value of this part, KXX, and plus the mean value of KYY, this part, okay? And minus 2 times mean value of KXY, 2 times mean value of KXY, okay? So once we obtain the kernel matrix, here, so we can easily obtain the value of MMD here, okay? And if we want to ensure the unbiased estimator for MMD, we just need to delete the diagonal, okay? It's just use statistics. And this is a kernel MMD. This guy is our statistic used in the TwoSample testing, okay? Yeah, and another method is called a classifier TwoSample test. In classifier TwoSample test, the idea is very easy. If two set samples are from different distributions, so we can expect a classifier. This classifier can classify two sets of samples, okay? Yeah, look at this example. If our two sets of examples are from all from real minst, okay? So, and we train a classifier to separate real minst and real minst. We know we cannot do that. So the accuracy in the end will be around 0.5, right? Yeah, will be around 0.5. If they are from different distribution, like real minst and generative minst, the accuracy will be larger than 0.5. So the classifier TwoSample test, the idea behind the classifier TwoSample test is very easy. We can just use accuracy as our statistics, right? Yeah. To say if two sets of samples are from same distribution or not, okay. Okay, now we have introduced two research lines for the TwoSample testing, for TwoSample testing methods. So which line we should follow and for the future development?
Feng, can I ask a question?
Yeah.
So for this permutation testing,
yeah,
could we do something like pick random bounded functions f and then see if the expectations?
You mean in the permutation testing?
Yeah.
Yeah, in the permutation testing, we will not do that. In permutation testing, we can look back.
Yeah, that lemma, what was it called? The MMD lemma, was it called?
It's in permutation testing, we have a statistic here, right?
Mm-hmm.
Yeah. So MMD is just a statistics, and permutation testing is independent with what kind of statistics you choose. Yeah. In permutation testing, we just permute our data and obtain the new statistics.
Because in the lemma, could you go to the next slide?
Yeah, we can go to the lemma. Yeah.
The previous one. Yeah, this lemma.
Yeah.
If you want to use this, because if for one function this doesn't hold, then we will know that they are not equal, right? So could we pick random bounded functions and see if the expectations are equal? If not, we pick another random one, and then until we get enough confidence, we keep picking random functions f, and then.
Yeah, I think if you want to do that, you will change this basic definition, right? Here we actually choose a sup norm. It means the largest value among this function, among the function class, right? If you random choose one, I think we will change the sup norm. Yeah, but that value will be less than this guy. Yeah, will be less than this guy. Yeah, and that means that value might be 0, but this guy is not 0. So P and Q are still from different distributions.
Yeah. So the one that I'm saying is kind of like probabilistic approach. So you just pick random f's over and over again until you get enough confidence that they are equal with certain probability, I guess. Like, I don't know.
Yeah. I think if we choose random thing, we need to analyze their bound in probability, right? To say what kind of probability we need to ensure we can obtain the good result, right? Yeah, that's an interesting proposal.
Okay, thanks.
Yeah.
Thank you. I have a question. What if the training dataset and the testing dataset of the same user is imbalanced? How does the method works? And have you experiment that?
You mean in the testing procedure?
Yeah.
What's the training set and test set?
They are imbalanced. They are different in the quantities, and also in practice, they may also have a slightly different distributions. So how does the method work in that case?
I think for testing method itself, it does not. It will. I think it does not affect on the imbalance. Yeah, because if we have 10,000 and we have 1,000, right, and we can still do this kind of permutation and obtain the value, but the result might be not powerful. Yeah, because we lose some information on the other side, right? Yeah. Yeah, okay. So I can continue. Wait a moment. Okay, now we have introduced two methods. One is called MMD, another called classifier TwoSample Test. So which one is best? We should follow in the future. In the next section, we'll talk about actually the classifier TwoSample Test is just a special case of kernel TwoSample Test. If we just choose a different, choose a purple kernel function, okay. If we consider using the kernel in MMD, using this kind of kernel in MMD, okay, here it's just a sine kernel. It's one here is a function, is a sine function. Yeah, it means fx is greater than 0, it will output 1. Instead of it will output 0. Okay, if we consider this kind of kernel in MMD, actually the classifier TwoSample test is equivalent to MMD test. Okay. And in the classifier TwoSample test, sometimes we will not use this kind of. Sometimes we will directly use the output in the last layer instead of the accuracy in classifier TwoSample test. For that case, if we consider our kernel as a linear kernel, with just time fx and fy is a linear kernel, the C2STL is another version of the classifier TwoSample test. It will be recovered by MMD test as well. Okay, so it means that the classifier TwoSample test, although they look very different from kernel TwoSample test, but actually they are special case for the kernel TwoSample test, for the kernel MMD. Yeah, we just choose different kernel function, so MMD can cover the classifier TwoSample test. Okay, so it motivates us to consider what is the best kernel in kernel TwoSample testing. Okay. Okay, first of all, we will look at what's a current choice in the kernel TwoSample testing. In the kernel TwoSample testing, we often choose we need to choose a characteristic kernel or called universal kernel to ensure the MMD has good property. Normally we will choose Gaussian kernel or Laplace kernel or called MQ kernel. Okay, all of them are translation invariant kernel. What is a translation invariant kernel? In translation invariant kernel, if we move x and y towards the same direction with the same instance, the kernel value will not change. It is called translation invariant kernels. Okay, it means that for this kind of kernel, the relationship between 2 points, x and y, will not change across the whole space. Okay, the relationship between them or similarity between x and y will be the same across the whole space, have the same behavior. Okay, have the same behavior. However, this kind of same behavior might let us give the same weight to look at difference between two distributions. Okay, and then we will use one example to show what's a drawback of these simple kernels. Okay, here we consider two sets of samples. It's called blob example. It's all of them are Gaussian mixture. On the left side is a Gaussian mixture, but there is no direction on each component. For the right side, for each component, yeah, it has different directions. Okay, it's different Gaussian mixtures here, P and Q. Yeah, if we use a Gaussian kernel to say the similarity, we'll find that the count of Gaussian kernel will be a circle around this point, around each central point. Okay, it's a count of Gaussian kernel. In this paper, we consider deep kernel. If we use a deep kernel instead of Gaussian kernel, like we introduce deep neural network to our kernel function, our contour will be this kind of thing. Yeah, you can say for this kind of contour, it will actually focus on some certain area instead of the circle area. For the circle area, actually they have same weight. They behave same way. They have same behavior across whole space. However, if we choose deep kernel, deep kernel is also non-translation invariant kernel. It will behave different way across whole space. Okay, it will provide us, let us know which area we should more focus on if we use deep kernel. Yeah. Okay, and then we have shown the motivation. Like if we consider deep neural network into our kernel function, the contour will change, will become this non-translation invariant kernel, and will actually have a different way to different area across the space. Okay. Now let's think about how to design a deep kernel for TwoSample testing. A very easy way to design this kind of thing is this guy. Okay, here is a phi omega. It's just a deep neural network, and we just introduce phi omega to our kappa. It's a kernel function like Gaussian kernel. So we can call this guy as a kernel, as a deep kernel, right? As deep kernel, we just embed deep neural network into our kernel function. Yeah. However, if we directly use this kind of design, it will cause two problems. The first problem, the k omega xy will not be characteristic, will not be universal. What kind of issue it will cause? Yeah, it will cause this kind of issue. In this case, P and Q are different. If our kernel function is not characteristic, it means or not universal, MMD PQ will be 0. MMD PQ will be 0. It means MMD PQ will be 0 even if P is not same with Q. Okay, it is not what we want because MMD itself, the lowest value of MMD is 0. Okay, yeah, and the smaller value of MMD means a closer distance of between two distributions. Okay. Yeah, so it is not a good thing. And the other drawback is this strange contour here. If we use this direct design, the learned kernel may consider extremely far away inputs as too similar. Okay, so this three contour, the point inside this three contour will have very high similarity with this middle point. It does not make sense, and actually it lost some geometric property for our data. Okay, it is not good. So how to design a good deep kernel to avoid two drawbacks here? Yeah, here is our proposal. Okay. Yeah, here we introduce epsilon q. You can say, yeah, there's a 1 minus epsilon kappa and plus epsilon and times q outside. Okay, so first we introduce epsilon q. Q is Gaussian kernel. So we plus epsilon q to our design because Q is a Gaussian kernel as a universal. So for any kernel function, if we plus a universal kernel, finally it will become a universal kernel. Okay, so we just plus epsilon q here, and epsilon can be a very small value. And in the meantime, we time our kappa and q. Okay, time kappa and q. Time kappa and q, we can ensure that although the deep kernel can learn the very focused contours. Okay. However, if we time q to our kappa, it will not consider extremely far away point as too similar because we give some restraint here. We give some constraint here. If we time our kappa and Q here, okay. So if we consider this kind of kernel architecture, yeah, first the K omega xy will be universal or characteristic. Yeah, can ensure MMD is a valid statistics to compare to distributions. Okay. And in the meantime, it will prevent the learned kernel from considering extremely far inputs as too similar. Okay. Yeah, because kappa times Q. Okay, kappa times Q. Okay. Okay, now it's a kernel design for our deep kernel, for our deep kernel. Okay. Any question? Yeah, if you want to discuss. Yeah. Yeah, epsilon is learnable. Yeah. It's learnable. Yeah.
So we get the square bracket. It looks like the square bracket.
You mean here? Yeah, there is. Yeah. It's like if we expand this formula, it's 1 minus epsilon times kappa times Q plus epsilon times Q. It's because if you plus epsilon Q, it will ensure our kernel is characteristic. Yeah. And kappa times Q will prevent the learned kernel from considering extremely far away inputs as too similar. Yeah. Okay. Okay. Now we introduce our kernel architecture. Next thing is how to learn it, right? What kind of objective we need to consider. Yeah. Here we will use the approximate test power of MMD as objective to help us optimize the parameters in our kernel, in our deep kernel. Okay. First, let's say the test power. Because it's a test power under H1. H1 means that P and Q are different. Okay. If P and Q are different, okay. We know we can obtain the MMD. We know the asymptotic distribution of unbiased estimator of MMD will follow a Gaussian distribution, normal distribution. Okay. Yeah, and then we can analyze the test power. Why we can call this as test power? Because P and Q here are different, right? So, and as here R is a positive constant. So this probability will approach one, because P and Q are different. So MMD must be a positive value, right? Yeah, but MMD cannot be 0. So this kind of probability should be close to 1. Okay. If this close to 1, it means we have very high test power under H1. Okay. Yeah, because we know the asymptotic distribution of MMD's unbiased estimator is a normal distribution. So we can compute this guy approximated by this thing. Okay, here is a capital Phi is a CDF of a standard normal distribution. Okay, yeah, and here is inside term. Okay, look at this term. And we know the CDF is a strict increase, right? It's an increase function. Okay, and we want this guy to approach one, right? So if the inside of this capital Phi is larger, it means that it will approximately approach 1, right? Yeah. And we can look at the inside here. Yeah, here we have two terms. First term is related to the square root n, right? And second term is related to the 1 over square root n. Okay. And R is a constant. So we know if we have the relatively large n, we know the first term is actually greater than the second term, right? Yeah, second term. So we can only use the first term to help us maximize the test power. Okay. Square root n here is a sample size. We cannot change it. If our problem is fixed. Okay, if our data is fixed. So we want to maximize its coefficient, MMD square over its variance. Okay. So our objective is here. Our objective is MMD square over MMD square's variance. Yeah, it is our objective. And we want to maximize this objective If we maximize this objective, we will get the higher coefficient to the square root n, okay? So it means this guy will approach to 1 with a higher rate, right? Yeah, so this is our objective. And then our K to learn a deep kernel is to maximize this J lambda hat to maximize the test power, okay? And for the estimation of the variance of MMD square, we will use V statistics. It's more stable in practice, okay? Yeah, in the literature, some of my friends, they will use U statistic, but empirically, it will fall for many times because the U statistic is not very stable to compute this variance term, okay? Okay, now we propose a objective to learn our kernel function, okay? So the theoretical question is that is the learned kernel will be the best kernel, right, in probability. Yeah, in this paper, we obtained some good result here. We found that the approximate test power uniformly converts to the population test power, okay? And the second, our learned network parameter is close to the optimal one, okay, if there is a unique best kernel. And the maximizer of J lambda hat converge in probability to omega star, okay? Yeah, and our theory is more general, can be applied to the bandwidth selection or classical multi-kernel learning. Yeah, it's a bandwidth selection means I think the Gaussian kernel, we always have bandwidth. We have bandwidth, okay. And bandwidth affects a lot in practice. So we can also use it to select bandwidth or optimize bandwidth, okay. Yeah, if there is a unique best kernel, omega star, and the maximizer of converts in probability to omega star, okay. And in this result, this guy is a J lambda hat. This guy is J lambda hat, and this guy is J. It's J. Okay, it's J lambda. It's J. Okay. Yeah, and we can find that this will be bounded. This will be bounded by this term. Okay. Yeah, and it will converge to 0 if we got a large n here. Okay. Yeah, here are assumptions we used in this paper. It's all the very regular assumption. Okay, first is a kernel can be bounded. A Gaussian kernel can be bounded, right? It has highest value. Okay, and the second is a possible kernel parameter lying in a Banach space with dimension d. Yeah, and the third one is a kernel parameter is an ellipsis. Okay, yeah. Once a kernel is it's like normal kernel, we know it can be, it can satisfy the third assumption as well. Okay. Okay, and for more technical details, you can check our paper or send the email to us to discuss. And then we will show the experiment. We'll show experiment for our method. Okay. Here we consider 4 baselines. The first is MMD. O is MMD with a Gaussian kernel, and for Gaussian kernel's bandwidth is optimized. Okay. And the second is C2ST, classifier TwoSample test. We have two methods here. The first method uses accuracy. The second method uses logits in the last layer of the neural network. Okay. And ME and SCF, they are just SOTA methods. Okay. Yeah, it's a result on the blob example. We have shown blob example previously. Okay. In this example, the C2STL and our MMDD, they actually have the similar performance, Yeah, but in the end, we are more stable when we have more samples here. Okay. Yeah, and it is another data set. It's called high dimension Gaussian mixture. Yeah, in the high dimension Gaussian mixture, we consider we have 2 components in our Gaussian distributions, but dimension is a little bit higher, and we will only change the covariance between two variables. Okay. Yeah, from this figure, we can say our method in the end has a very high test power if we increase the number of samples we have. Similarly, if we increase the dimensionality of our data, yeah, our method, this red line, still have a very high test power compared to other methods. Okay, and then we answer the question and at the very beginning, if CFA 10 and CFA 10.1 from same distribution, the answer is not. The answer is not. Yeah, you can say actually for many methods, previous methods, they tell the same. They tell the same thing. They're from different distributions. Yeah, because here we said the alpha is 0.05. So if the reject rate is higher than alpha, we can say it's from different distributions. Yeah, and we can say our methods have very high reject rate here. Okay, compared to other methods. Yeah. Okay, in the previous experiment, we consider our deep kernel and compare it with a very simple version of previous TwoSample test methods. However, we can still consider more deep kernels. Like we can consider the sine kernel or linear deep kernel, Gaussian deep kernel, or our deep kernel. Okay. And we can also consider two objectives to optimize our deep kernel's parameter. First is to maximize our test power, approximate test power. Second is to minimize the cross-entropy loss between two sets of samples. Okay. Yeah, and based on this frame, the S plus C is actually C2STS, and L plus C is C2STL, D plus J is MMDD. Okay, our method. Okay, from this result, we can see that the performance will be generally higher, better if we move from sine kernel to linear kernel to Gaussian kernel to our deep kernel, and if we consider maximize the test power instead of minimizing the cross entropy, we will get the higher performance as well. Yeah, from this figure. Yeah, from this table. Okay. Okay, yeah, that's all for first work. Yeah. Any question? Or I can just move on to the second one.
Yeah, so I'm wondering, so you showed this evaluation for these different distributions, right?
Yeah,
this
yeah.
blob and all this, but what can you say about general distinguishing between a general adversarial distribution like the one in the example?
That's the next work.
Okay.
Yeah.
Okay.
Yeah, for next work, it will be quicker because we have a lot of background here. Yeah.
Okay, yeah.
Yeah.
Any other questions? Yeah, just as a reminder, I think we have about like 10 minutes left.
Yeah, okay, I think we can make it. Okay, we can move to the next. It's maximum discrepancy is aware of adversarial attacks. Yeah, it's grateful to work with Razor, Jinfeng, Bo, Tongliang, Gang, and Masashi Sugiyama. Yeah, it's a adversarial attack. Yeah, and why it can be successful because they have different distributions, cause a significant error here. Okay, and then in the previous work, actually, the Nicholas Kalanis paper, he showed that the MMD test is unaware of adversarial attacks. Yeah, so we have a nature question. Nature and adversarial are really from different distributions, right? Because MMD test as a statistical test, if it is not aware of the difference between adversarial and nature, so which one we should believe, right? Yeah. We gave the affirmative answer. They're from different distributions. Yeah. And we found that the previous use of MMD test on the purpose of missed the 3 key factors. Factor 1, in Kalanis' paper, he used the limited representation power of the Gaussian kernel. And second, they overlook the optimization of the used kernel parameter. It's actually a very simple Gaussian kernel with bandwidth of 2. Okay, it will not work actually, obviously. And the third one, they do not consider the non-IID adversary data will break the assumption of MMD test. Okay. So in this paper, we introduce a new kernel, or introduce a new deep kernel. It's called semantic aware deep kernel, SAMMD, to replace the Gaussian kernel. And for second factor, we compute approximate test power using the partial data and optimize the parameter using our deep kernel. Okay. And third one, we consider use a broad bootstrap instead of a permutation test to help us obtain the good result, even if our data are non-IID. Okay. Okay, and first we will introduce the SAMMD test. Why we consider the semantic aware and what is semantic aware is based on this figure. We found that for the well-trained classifier, its behavior in the second to the last layer in the network, it's very different. If we look at use TSNE, you can say it's very different compared to nature data. Okay, here is the nature data. What kind of nature data we will look at in the second to the last layer? And here is FGSM, PGD, CWA, and square. Yeah, you can see it's very different. If we got this kind of samples, we can recognize they are from different distributions by human eyes, right? That means actually they have very different statistical property. Yeah. So instead of training our deep kernel from scratch, we will just use the network in our classifier, because in the second to the last layer, we can see the very different behavior here. Okay. Yeah, so our design is very easy. It follows our same design with our previous paper. Yeah, but we replace this guy as a semantic aware kernel. And here is 5P is just a part of classifier. Yeah, and it will extract the second to the last layer's features using 5P here. Okay. Yeah, and because we do not have any parameter to optimize here, right? 5P. So we only have 3 parameters here to optimize. Epsilon 0 and sigma 5P is a 5P of this guy. Okay, it's this kernel's parameter, like a bandwidth. Okay, and the bandwidth of Q. Okay, we only have 3 parameters. Okay, now we have 3 parameters. We need to optimize it. Okay. However, in this case, we consider sometimes the adversary data, they are non-IID, right? They're not IID sometimes. Okay, non-IID. So we need to refine the previous theory to see if the previous test powers, previous asymptotic will still follow. Okay. So here we consider Y from a statistical process. Okay. Yeah. And finally, we got the similar answer. Okay, so we can still use this kind of test power. Yeah, this kind of test power to maximize the test power to obtain the optimal parameters of our deep kernel. Okay. Yeah, and we know we only have 3 parameters, so we will maximize this guy and to obtain the optimal 3 parameters in our deep kernel. Oh, sorry. Yeah, and then we just move to the result. Okay, yeah, design is very easy compared to if we have a previous knowledge about last paper. Yeah, so it is a test power on different tags. Okay, and we consider different methods or different test set or PGD. And you can see our method always have a high test power here, because for the semantic features, yeah, it is very easy to distinguish between two sets of samples. Okay. Yeah, it's still have, if we change the test power on different epsilon. Yeah, if we change different epsilon for different methods. Yeah, and here we also consider what will happen if we got the nature data mixture situation, right? maybe in the bunch of data coming, we have the adversary data and the nature data, the mixed here, okay, mixed here, yeah. So what will happen under that case? And here is the nature data proportions in the mixture. You can say when we increase this nature data proportions, the test power in the end will get lower, okay, yeah, get lower, yeah. But we still have very high performance here, yeah. Yeah, and here we also consider what will happen if we introduce adaptive attack here. Yeah, it can be seen we still have a good result. Yeah, when we got tested on the nature, we have nature data in our set of samples. Okay, yeah, yeah. So that's all for second work. Yeah, it's like basic. It's like the application for the first work. Yeah, but it actually answered the important question like distributional discrepancy. Yeah, is the distributional discrepancy between nature and adversary data. It can be easily captured. Yeah, not we can always distinguish adversary and nature data. Yeah, in the view of statistics. Yeah, yeah, that's the most important thing we want to tell in this paper. Yeah. Okay. Yes. Yep. Thank you.
Thank you very much, Feng, for your interesting talk. Yep, there's a question there.
Yeah, thanks for the talk. And I have a question on the application because right now you're talking about adversary samples. So, but I'm thinking about like membership inference because membership inference is exactly trying to have a attacker classifier to distinguish the difference between the distribution of the members and the non-member input to find out, okay, whether this sample is a belong to the training data set or not, right? But the first question is, I mean, have you considered that? And the second question is that because they have assumption, membership inference has assumption that the reason why it can success because of the overfitting. So I'm wondering whether if the model is like more generalized, so which means that the overfitting maybe is not there. So will this kind of method still work on membership inference in your point of view?
I think we actually have the quite similar things current work about that. It's about the machine learning. Yeah.
Okay.
It's I think the main reason it's not TwoSample testing is about independent testing. In the independent testing, we will consider the difference between the joint distribution and the product distribution. Like we will consider PXY and PX times PY. Yeah, we consider the difference between this joint and product. Yeah, and under that case, we will consider if this data is used for training. Yeah, because if the data is used for training, and the embedding of this data for this train network, it will not be RID. Yeah, so we have something along this direction, but use the independent testing instead of TwoSample testing. Yeah, yeah, it's quite similar because it's independent testing is I think it can be called as another application of TwoSample testing because we test the joint, the difference between joint and the product distribution. Yeah.
I get two questions as well. So for the first one, I think is this any possible like using this testing as like discriminator to generate adversary attacks examples?
Yeah.
That's it can be like indistinguishable, for this most test. Is that possible? Like using this?
Yeah, it's possible. Yeah.
Okay.
Actually, in the first work, I showed the connection between classifier TwoSample test and MMD, right?
Okay. So
the classifier TwoSample test can be regarded as a discriminator in the GAN.
Yes.
So
kind of thing.
in theory, we can replace MMD. We can replace classifier discriminator in GAN with MMD. Yeah.
So can I like to the previous slides? Like
previous slides.
Yeah, the mix. Yeah, this mixture of adversarial data and natural data. So it does this picture implies that adversarial training works. Like if we do the adversarial training to protect the like attack, so after the training, it will be indistinguishable for the test. Like
What do you mean? Here we
yes,
do the
for the
adversary
I mean, like if we use adversarial training, like to mixture the data, right? To like for the training, so the test won't like distinguish the previous clean data and the adversarial examples, right? Like,
you mean if we use a mixture, mixture data for the adversary training?
Yeah.
For the adversary training, and what's the result? It's we got a higher robustness. Or...
Yeah. So where this like imply a bit of this. Or because from this picture, I think it cannot answer the question like they are from the different distribution if you mix the adversarial data with natural data.
Yeah, it's still different because we mixture it. Yeah.
Oh yeah.
So the mixture of nature and adversarial data, has a different distribution compared to the adversarial data distribution or nature data distribution. Yeah.
Okay. Thank you.
Yeah. Thanks.
Any last question, Romano?
Yeah, so for example, in this test, so what model do you use for the adversary distribution? I mean,
You mean our classifier?
So first of all, the distribution that you test with, right? To get this red graph.
Red graph.
What is the one with the 1, right? So what is the actual adversarial distribution you use for this test? What is the model for that?
Yeah, here.
I mean,
I forgot the detail, but probably PZD, I think. Yeah.
What I mean is, what I'm trying to ask is like, what assumptions does your classifier make about the adversarial distribution or the class of distribution? I mean, are there distributions that can still fool your classifier, or does your classifier depend on this assumption or not?
Yeah, I think the adversarial example we generated in these two figures, I think should be PZD. Yeah. So it can fill our previous classifier. Yeah.
Okay, but for the new classifier,
what do you mean the new classifiers? Because here here we consider we do not train a new classifier here. Yeah, so it's just a classifier trained with the nature data.
Okay.
And we use that we use that classifier to construct our deep kernel. And then in the upcoming batch, we might have in this batch we might mix the nature data and the adversarial data, right? And we want to tell if they are from nature or not.
Yeah, but suppose you don't do the mixture, you just have 0% natural data. So I think it's your previous
0% nature data means in the upcoming batch of data, they all are adversarial data.
Yes.
Yeah.
So what distribution does this come from? What adversarial distribution? I mean, when you do these tests, you are assuming something about that distribution, no?
In the TwoSample testing, because it's non-parametric TwoSample test, so we do not assume the type of distributions. Yeah.
Okay.
Yeah, we do not assume type of distributions. That's a non-parametric TwoSample testing means. Yeah. So we only have 2 sets of samples, and we want to see the difference between them. Yeah.
Okay. Yeah, but what actual distribution do you use, or how do you generate?
The adversarial samples are already generated in this CFAR 10.
CFAR 10, yeah.
Which one? Sorry.
CFAR 10, yeah, it's generated on the CFAR 10.
It's this particular distribution.
Yeah.
Okay.
Yeah.
Okay.
Yeah.
Yes.
Oh, sorry, I misunderstood your question.
Sorry, I misunderstood. Yeah, all right. Thank you. So, yeah, I guess the follow-up question is, yeah, how do you think it will perform on other distributions? You know, not CFRT.
I think we test on other data sets as well, but for the slides, I didn't report it. Yeah.
All right, thanks.
Yeah, thank you for your question. Have more questions? Or?
Yeah, I think we are out of time. So if anyone has any questions, they can stick around and then we can discuss the questions offline. Thank you everyone for tuning in. And thank you very much, Feng, for your very interesting talk.
Thank you.
Hope to see everyone in the next seminar. Thank you.
Thank you for coming.